Today we're going to pick up with section 12.1. When we ended our last class, we said that if you have evidence to reject the null hypothesis, saying that the means are not all the same, that we would need to design a contrast to make comparisons between those means. So a contrast is something that you set up prior to running your study and before you examine your data. So in your head, you might already know that the 12th graders eat more of the lunch served by the cafeteria than the freshmen. So the contrast might compare the freshman versus the senior before you start the study. You might also think that the freshmen throw most of their lunch away, where sophomores, juniors, and seniors maybe eat more of it for whatever reason. We might compare the freshmen to the sophomores, juniors, and seniors. The contrast really can be anything that you want, but it has to be formulated before you examine your data and before you start your experiment. If you don't have any preconceived notions before you examine your data or before you run your experiment, that's okay. When we're done with the study and we realize that the means are different, we can run a multiple comparison procedure, which is just multiple t-tests, to see which pairs of means are different from each other. It can be a tedious process, so this is why a contrast is a much better option than multiple comparison tests. Just like any inference test, we want to make sure that we meet the assumptions of the test before we proceed. So the ANOVA is going to be valid in some circumstances. And the first is that we have I, independent, simple random samples, one from each population. So if we were comparing the different grade levels and how much they eat in the cafeteria, we would need a simple random sample of freshmen, sophomores, juniors, and seniors. So we would need 4 independent SRSs. But you would measure the same response variable in each sample. So maybe what percentage of the lunch they ate or what percentage they threw away. The populations have a normal distribution, and we don't know the means for any of them. And the third criteria is that all the populations have the same standard deviation. Again, we don't know that value, but with each sample, we will run one variable statistics and we'll look at the sample standard deviation and the value of their X bar, and we'll make a decision there. So when we set up the model, we have what's called a factor effect. So this would be the differences between the different areas of interest. So again, maybe the sophomores eat less lunch than the seniors, or something to that effect. We've seen this model before, data equals fit plus residual. When it pertains to the one-way ANOVA, the factor effect is the fit. And then, of course, we will have some error or deviations from the norm. So this is the model that they'll use on your reference table. So for some number of I populations, so the subscript just represent the observed value from a certain population and whichever variable it's measuring. So here's the comparison of 3 different groups. We don't know what the mean is or mu, but the idea behind the ANOVA is, are the means all the same or are they different? So if you're just looking at these distributions, mu1 and mu2 are fairly close together. They're not identical, but then we can see that mu3 looks to be significantly different just from the model, okay? All the residuals or errors are going to be assumed normal. The parameters of the model that we're using are the different population means and the common standard deviation that will represent sigma, even though we don't know what sigma is. When you start this process, we do want to examine graphical data and numerical summaries on each individual subpopulation. So I want to know what the X-bar and standard deviation is for the freshmen. I want to look at a graph to make sure it's normally distributed. And then I would do that with sophomores, juniors, and seniors. If everything seems normal and the assumptions are met, then you can proceed with the ANOVA test. One of the options for comparing your data is side-by-side box plots. This will allow you to look for data or errors that are between the groups and then within the groups themselves. This is one that I took from our book. So in A, if you look at each of these models, they do seem to have a lot of overlap, and the medians don't really seem that different, although they're close. For B, the way that it's drawn, it looks a little bit more convincing that the medians are significantly different. Looks like they're starting to fall at the end of each distribution. So group B looks a little more possible of having different means. So we said that the ANOVA model assumes that the population standard deviations are all equal. In fact, they're not going to be equal. Most of the time, they're going to be close. If the standard deviations are not exactly equal, the ANOVA procedure is not sensitive to that. The sample sizes then should be the same or similar. So if the sample sizes are extremely different and the standard deviations are very different, then this is not a procedure we want to use. Now, when the standard deviations are not equal, what we can do is take the largest standard deviation, and we want to make sure that it's less than twice the smallest standard deviation. If this criteria is met, then it is safe to use the assumption that all the standard deviations are equal, and we can proceed with the ANOVA process. So we want to first set up our null hypothesis for one-way ANOVA, and it will basically say that all the population means are the same. So we set it up so the null, so mu1 equals mu2, and so on. So you'd list every single mu here. You don't provide an exact value, you just state that they're equal. The alternative hypothesis will say that the means are not equal, and you can write that in words. And remember, when we finally have evidence, it could show us that the means are different. Doesn't mean that they're all different. It could just mean that at least one is different. And then we'll use graphical data and other methods to confirm that. Because we don't know standard deviation, we're going to use the sample standard deviations to estimate sigma. If we assume that all the standard deviations are the same, it makes sense then that we use a pooled method for sigma. So we're going to combine all of the samples into one single group and go from there. When you pool, you just have to be careful. If you have unequal sample sizes, and quite often you will, a sample size that's larger, say has 50 samples, will have more weight in the pooling process than a group that only has 10 observations. So it does give more weight to the bigger groups. So in our problem, it's likely that we will be provided the sample variances from each of our populations, and they'll also tell us the sample size for each of those populations. So this is the formula we would use for the pooled sample variance. This is on your formula card. It looks messy, but basically it's saying S to the second is variance, P is pooled. We'll take our first sample size, N1, and we'll subtract 1. And we're going to multiply it by the variance or the squared standard deviation for that first group. And then we're going to add the next group, and it will be sample size N2 minus 1 times that variance or standard deviation squared. So the entire numerators will be the sample size times the variance. In the denominator, it's each sample size minus 1 until you have the sum of all. And this is considered an unbiased estimator of the variance for sigma. There's no homework problems associated with this lesson. If you have any questions going through these notes, please make sure that you contact me. Otherwise, have a great day.